So thanks. I'm honored to lead off this series. In retrospect, I wonder if I need a little more background information on what's going on. I'll try to talk through a little bit of the background of this story. I also wanted to note there's a lot of people who have contributed to the pieces that I'm going to take you through. And interestingly, we first gave this as a team talk at Ameriflux. And since it was a remote meeting, we could have a team talk. And I actually had two undergraduate students, a master's student and a postdoc, who all contributed to this. And I could never have flown them all across the country and afforded it. So it was great that they could all do this remotely. They're not on today, but some of their names are up here, and I'll show you some of their work as we go. And one of the students actually just started college and did the work as a high school student with us. Quite remarkable. So a little bit of the background. In the US, there has been a push, mostly by the National Institute for Standards and Technology, to instrument cities with greenhouse gas measurements to infer urban emissions. And the cities in red on this map, LA, Indianapolis, and Baltimore, Washington, which is kind of combined, are the three NIST test beds. NIST is the National Institute for Standards and Technology. And their objective is to develop ways of verifying greenhouse gas emissions from urban systems. And I've spent many years working in Indianapolis. We actually started measurements there in 2011. And this inset shows the mole fraction measurement networks in each of these cities. And as is typical US style, these were all developed somewhat independently and a little bit based on local investigator wishes. So they don't necessarily look coherent in the methodologies, but it's good for experimentation. And the basic approach is to measure what we call the enhancement in the greenhouse gases. That is downwind minus upwind, concentration downwind of the city compared to the concentration upwind of the city. And that difference in concentration gives us information about the emissions from the city. Sounds very straightforward. As usual, what sounds simple is not necessarily always that simple in practice. But nevertheless, we can use those sorts of enhancements to solve for emissions using either simpler atmospheric budgets, such as we often do with aircraft flights, or more complex atmospheric inversions, which Thomas Laveau, who has worked with my group for a long time, has done some of those for the Indianapolis data set. So that's been the basic approach. Now, I started my career in carbon cycle work doing flux measurements up here in northern Wisconsin. But those are eddy-covariance flux measurements, not these kind of atmospheric budgets. So, what about flux towers? How can they be used within this context? In the US community, research community, these two approaches have somewhat diverged. We have people doing urban mole fraction measurements and mass balances, and people doing eddy-covariance measurements, and they have not come together that much. So I've been trying to bring these communities back together. And so I gave this talk first at Ameriflux with the intent of opening that community up to thinking about these urban eddy-covariance issues. I think the European community has been ahead of us in that regard. You've been making urban flux measurements for a longer time, but maybe you'll find something interesting and a little innovative in what we're trying. So I argued to Ameriflux that the purpose for these flux towers in cities is the same as our purpose for ecosystem flux towers. Ecosystem eddy-covariance measurements measure fluxes continuously. You get high resolution in space and time. We collect data about the ecosystems to understand what's controlling the fluxes, and we develop and test process-based models. We know that the area that they measure is small, but the data is very rich and informative about the process models. And I would argue that that becomes part of our bottom-up picture for ecosystem fluxes. We simulate using process understanding. We then often merge this with top-down information from the atmosphere, atmospheric inversions or atmospheric budgets using mole fraction measurements. And that's exactly what we want to do in the city, same sort of process. And some folks have argued that the urban systems are too complicated, and I would say no, they're not. And I think we can prove that they're not, that these measurements are useful in this venue. So I'm going to try to illustrate 4, 5-ish purposes here. 3 bullets. Understanding the processes, evaluating the process level understanding of anthropogenic emissions, not ecosystem fluxes. But then we also need to understand the urban region ecosystem fluxes, not just in the city, but also outside the city. And then finally, a simple example of using these fluxes to flux measurements to evaluate the atmospheric models that we need to understand the greenhouse gas transport in the urban environment. So that's my agenda. And whenever I take a breath, do not hesitate to interrupt me with questions if you wish. I like questions. So this is a map of the measurements that my group has deployed to eddy-covariance flux measurements, not the greenhouse gas mole fraction measurements, to study systems around Indianapolis, and we're merging into work with the Baltimore-Washington group as well. And some of these measure grass, some measure agriculture, some are urban settings. And one is an Ameriflux site that we've adopted because it's close by and useful. And I'll show you a little bit of results from each of these. And so first off, process level understanding of anthropogenic emissions. We've just submitted this paper, and I'll go into what we're doing here. But first, to back up, you might say, well, wait a minute, if you're doing an atmospheric budget over a city, doesn't that test the urban inventory? Why do you need a flux tower? And I'd go back to that analogy with ecosystem fluxes and inversions. We don't tend to use continental scale inverse models to evaluate the process level understanding in our ecosystem models. We might compare the net fluxes over large areas in space and time and see if we're consistent. But large scale inversions are difficult to use to test process understanding. Flux towers give us very high spatial and temporal resolution. Now, their weakness is they don't see the entire landscape, but that's their weakness. Their strength is the temporal and spatial resolution. The inversions can give us the large area. These are complementary, they work together. So I think we do need flux towers in this system and understand our process level understanding. Now, which model are we using here? We're working with the Hestia model created by Kevin Gurney's group. Kevin's now at Northern Arizona University. Its default is square kilometer resolution. We actually got it down to 200 meter resolution. It's hourly, it's sector specific. We've compared it to urban inversions at citywide scale with very good success. Laveau et al. Showed less than 3% difference between the Hestia inventory and our citywide CO2 inversion. It was quite remarkable. Turnbull compared aircraft inversion and inventory, also very successful, less than 10% divergence. But the high spatial and temporal resolution information that's in Hestia has not previously been tested. So we wondered, does all this detail look like what we could measure from the atmosphere? So that's where we're coming from there. So I'm going to zoom in now on site 2. We have very uncreative names for our mole fraction towers, 1 through 14. We only have had 12 running at one time. But some of them, site 2, 3, and 7, we have instrumented in both ways, mole fraction data and eddy-covariance flux measurements. And so site 2 is on the east or roughly downwind side of Indianapolis. It's in a mixed urban-suburban system. You can see an interstate highway here, suburban area with lots of trees here and some kind of intermediate development in the middle. So this is the site. We had a flux tower on there running for 6 to 8 months. It was a student experiment. It didn't work as well as we hoped, just in terms of instrument failure. But we got enough data to make hay with this data set. And this is part of Kai Wu's work, which is just submitted again. And so start with the basics. The flux data show what you would expect for a mixed biological and anthropogenic CO2 flux signature. This is CO2 flux versus hour of the day, composited over multiple months. Cold season in blue, that's January, February, March. Warm season in red, April, May, June, July. And you see traffic peaks in the cold season, all positive in the cold season, all emission, which makes sense. And then in the warm season, as things green up, you see a signature of photosynthesis in the middle of the day, but still these photosynthetic peaks, traffic related peaks. If you break this down as wind direction, this is a flux rose. So the radial axis is wind speed, and the polar axis is wind direction, and the color is CO2 flux. Blue is net photosynthesis, red is net emission. And when the wind comes from the highway, clearly there's much higher positive fluxes than when the wind comes from the suburban area, where in the warm season, you even see net photosynthesis. So this makes a lot of sense. This looks like we've got the right data coming in here. But this is total CO2 flux. I can't compare that to Hestia. I can't, sorry, I like to say torture models for a living. I can't torture the Hestia model with these data sets because it's not a one-to-one comparison. So we have to decompose these fluxes into biological and anthropogenic components. We're doing this using CO-CO2 ratios. And further, we want to decompose these fluxes in space as well as time so that we have a pixel-to-pixel match between our flux measurements and the model. Then we can put together an apples-to-apples test. So I'll show you some results from that. So, sorry, this is animated. I'm just going to blow through the animation because I don't like animations. All right, so we have a flux gradient relationship that we use. We compute the eddy diffusivity by measuring the flux of CO2 and a vertical gradient in CO2. We then infer the flux of CO using that eddy diffusivity and a vertical gradient in CO. We don't have a CO flux measurement. Thinking about doing that directly, but we don't have it at present on our tower. Then by knowing the ratio of CO to fossil CO2, which we derive from flask-based 14 CO2 measurements collected at the tower and also at an upwind tower, we can convert the CO flux into CO2 fossil fuel flux. And then by subtracting that from the total flux, we can get the biological flux as a residual. Does that work? Show you some results. So again, this is the area. This is a sample of a single flux footprint. We're not using a fancy flux footprint approach. You'll hear about more advanced methodology from Ankur Desai in a couple of meetings, and we should use his technology, but we're not there yet. This is a map of fluxes from the Hestia model of the same domain, and you can see the highways and the pretty good spatial resolution of the Hestia emissions. This is just the anthropogenic emissions, which is what we're going to compare to directly here. So the decomposition, cold season on the left, warm season on the right, using the CO to CO2 ratios and a CO to CO2 fossil fuel ratio of 9 parts per billion per part per million based on the flask sampling gives us the following. This is the blue is the total CO2 flux, cold and warm season. The red is the derived fossil flux, and the green is the derived biological flux. And it looks pretty reasonable. The one thing you might raise your eyebrows about is the photosynthesis in the winter. I'll come back to that. And I'm just taking a look at the chat. I'm sorry, I'm going to let my hound dog in while I talk to you. Yeah, Hestia is a combination of inventory and model. It uses inventory data, fuel consumption, CO emissions, information about the natural gas distribution network, traffic data to construct an estimate of emissions. The inventory data is relatively coarser in space and time than the model product, because then process level understanding of how people work and perform and behave over time and space is used to fill in the gaps. And so that's why I call it a model. It's based on inventory data, but it's not strictly inventory because you couldn't get the space and time resolution with only the inventory data. So it's a hybrid. Thanks. I'll try to keep an eye on that chat too. So this is what the decomposition looks like. It looks quite reasonable. I'm going to knock off the chat for the moment. I'll see the bubble if it appears because I can't see my screen if I have the chat up too. Here's the difference between Hestia and the eddy-covariance fluxes. So the top panel just shows the half-hour by half-hour differences. CO2 fossil fuel flux aligned with Hestia half hour by half hour, pixel by pixel, added up. The biases are very small. If you don't speak micromoles per square meter per second, trust me, these are small differences overall. The spread is pretty large, and I would guess that's probably a large part sampling error from the eddy covariance methods. The most remarkable part is when we look at the composited fluxes versus time, Hestia versus fossil fuel, cold season on the lower left, warm season on the lower right. These are incredibly similar. I almost don't believe it, how closely these agree. It's remarkably good. Do we detect reduced emissions on weekend and vacations, Michelle? I think so. We haven't tested that part. That's a very good basic question, which we should do. I'll show you another activity change result in a few minutes, though, but the simple one of weekends we haven't done yet. My bad. But this looks incredibly good. We're very encouraged. And the other part is that Hestia looks great, right? This is incredibly encouraging to me that these two things converge. So I would argue for this kind of a first high resolution space and time comparison between inventory / model hybrid in the data. This is very encouraging. Hestia is really hard to build, but it appears to pay off. It appears to work very well. And the flux decomposition approach also appears to be doing its job. And this combination, if you know flux measurements, you know that we don't tend to trust any one approach as the truth. We tend to look for convergence among multiple methods. This lends confidence in both approaches to me. We don't yet have such a super high resolution urban ecosystem model yet to test, which is interesting. I need to work on that. So I'm going to kind of sideways answer Michelle's question. Do we see changes in fluxes when stuff happens? And we went after a big weird stuff, which was the lockdown due to COVID. And this is Vogel et al. In preparation. It's not Felix, though, who I saw on the call. It's Eli, who is an undergraduate student at University of Maryland, Baltimore County. We've been taking advantage of the pandemic to bring in undergrads from all over the country who want to work with us, which has been cool. So Eli did this just in a summer and then has been following up with a couple of semesters of research afterwards. This is another one of our mole fraction towers, Tower 7. It's on the west side of the city, has a highway to the east and a suburban forest to the west. And we were targeting the suburban forest since usually we have westerly winds. Well, we had this set up when COVID happened. And so we were sampling the easterly winds to see if we could detect changes in traffic. Not as much data as we would hope if this was optimally placed to sample the traffic, but it was what we had for this event. We didn't have another tower running at the time. Again, we have a CO2 vertical difference as well as an eddy covariance flux measurement. And we don't have the flask sampling at this site. And so we've experimented a little with the CO2 fossil ratio to see what happens if we tweak it. We used Apple mobility data to define the lockdown periods prior to lockdown in February, lockdown period in March and April, all largely pretty biologically dormant for this part of the world. The total fluxes versus hour of the day aggregated over those time periods look like what you might expect. Traffic peaks and a much reduced traffic peaks and much reduced flux levels during the lockdown. This is only sampling easterly winds coming from the highway, but not yet doing the decomposition. And so to do the decomposition, we experimented and toggled that ratio from 4 to 15, which is 4 is much less than it should be. 15 is much more, but it's going to be in that range. And interestingly, our basic idea was that in February, with winds coming from a highway, we shouldn't have much biological flux. So it's an interesting way to test the ratio. And interestingly, a number of about 7 or 8, which is about what we're getting at the large scale from Jocelyn Turnbull's work, gives us about the 0 biological flux we're looking for here. And so the couple different ways of getting it are, which is an important parameter. If we use that number, we then can decompose. The result is there's not much biological flux. So the comparison looks a lot like those two original panels I showed you, you clearly see the drop in fluxes during the lockdown, even with the easterly winds and kind of poor sampling conditions because of the location of the tower relative to the highway. And very strong correlation with traffic pre-lockdown, weaker correlation with traffic after the lockdown, largely probably because the emissions are just smaller and the other fossil emissions are beginning to show up. So we think this demonstrates that even with, an event of order of magnitude a month with a poor wind direction, we can measure in pretty good time resolution the change in metabolism of this urban system. Hopefully the next time we do this, we won't be measuring a disaster, we'll be measuring an emissions mitigation effort. That would be our target. So tracking these events is difficult for the inventories. The inventory data doesn't necessarily come back with this time resolution or spatial resolution. The atmosphere is very good for that. Inversions can see these events in time also, but they have more difficulty being resolved in space. So all of these methods really do fit together to give a complementary story of what's going on. And Dario asks, do we have local emissions due to house heating? Yes, we do. Does it have the same temporal pattern as the traffic? That we do not know. We only know that from the model. And we have not been able to identify that explicitly from the atmosphere yet. I do not believe that in the model, it does not have the same temporal pattern as the traffic, but I have to go dig that out. It's a relatively smaller contribution from this flux footprint, but that's a good question. We should do more investigations of things like that. Exactly the track we want to head down with this work. So I'm going to go a little into biology. Biology is important. It's in the city. And let's see, Gara Villalba asks if I could say a bit more about the complementarity between modeling and inversions and flux measurements. Sure, I'll pause on that for a sec and just kind of repeat these statements again. Maybe they aren't, maybe they make sense, maybe not. I don't have a good graphic for this, but let's think of three different approaches at getting at these emissions and quantifying the system. One is the bottom up, the model with activity data, how many miles have been driven, how much fuel is consumed, where are the house heating systems, when are people home, when are people away, all that kind of stuff. You can build that into an emissions estimate. You can get wonderful activity information about where things should be happening in space and time, which is challenging from the atmosphere. I tell people, the atmosphere sees everything. That's a blessing and a curse. You see everything, which is great. But then if you want to say, well, what's here and why is it there and which source is it from? That's more challenging with the atmosphere. The inventory can disaggregate that information. We can try to disaggregate with the atmosphere using things like flux footprints and tracer ratios, which is what we're doing to try to then line these up to compare. Because our experience shows that inventories are often biased, not because of any nefarious reason, but because you can miss things and make mistakes and have systematic errors. And atmospheric verification is important if we can get it to be precise enough. Now that's a flux tower inventory model story. But again, the flux tower only sees areas of roughly a square kilometer. So if I'd like to measure the whole city, that's difficult to do with a flux tower because we just can't put enough systems out there. So to measure the whole city, it's good to look at the entire atmospheric mass balance as the air moves across the city. And then I can say the entire city of Indianapolis or Baltimore, Washington, or Los Angeles, or Toronto, where Felix Vogel is working, emits so much CO2 or methane, and compare that to the space and time integral of our inventory. And that's yet another level of comparison in these systems. With these multiple approaches and multiple sources of comparison, we develop more and more confidence in our numbers. That's the basic argument here. And Michelle, technical question of a non-expert in flux measurement. Do we need it on a tower? What if we had it at the top of a building? Buildings give me a little bit of worry. Why? Because One, there's quite a bit of flow distortion from a building. There still is some from a tower. I tend to be more willing to take risks with stuff like that. Others in the flux community will be more hesitant. That's one reason. Flow distortion might not make your flux measurement representative. The other point could be that if you're not very high, you see something very close, and you might end up measuring something like the exhaust from the building, which could be interesting if that's what you want to see. So let me more generalize that. If you have a low tower, you'll see close. If you have a higher tower, you'll see farther away. You may want to do either one, depending on your purpose. I'm going to show you results from a low tower next. Previous was big towers, communications towers. We didn't build any of those towers. They're all communications towers. We just put our instruments on and plugged in. But next I'm going to go low. Maybe this will help. All right, so going low, there's a low tower, right? That's not a big tower. That's a small tower. It's not a building top, but what we want to measure is turf grass, because there's a lot of grass in cities. And what does the turf grass contribute? So this is the flux instrumentation, solar panels. This is actually in a cemetery. We need to understand the ecosystem fluxes coming within the city region and how they impact the CO2 as well, because that alters the CO2 that we measure upwind and downwind, where we want to understand the anthropogenic emissions. There we go. So I'm going to show you results from one of these, but we've had 3 flux towers deployed over grass. One at NIST. I'm sorry, these are the wrong arrows. This one is the NIST campus picture. That one's still running in Baltimore, Washington. This is the golf course. They got that one right in Indianapolis, which is highly managed. And this is a cemetery in Indianapolis, the picture I showed you, which is very unmanaged, just mowed, but not watered or fertilized much at all. I think maybe none. And so here's a first cut. This is Indianapolis. And these are fluxes of grass in red, soybeans in green, and corn in blue. Corn and soybeans are all over the Indianapolis region, outside the city. And in the summer, of course, corn grows like crazy and the grass looks small. But in the winter, the turf grass is growing, which is remarkable and large flux. So remember, I showed you photosynthesis in the winter from Tower 2. We think that's correct, and we think it's turf grass, which is intriguing. So one of the things we're doing then is updating the parameters in ecosystem models we use to describe the within city fluxes. We've been working with a really simple model, VPRM. And this shows our high school student, now a college student's work, trying to improve the parameter optimization. And the most important thing we needed to do to get that winter photosynthesis was to eliminate or reduce the minimum temperature photosynthesis allowed in the model. The green is the optimized, the blue is the pre-optimization with a higher minimum photosynthetic limit. Red are all the measurements. They tend to be noisier. The model will never capture that. Obviously, the green does a better job than the blue at capturing the mean. We're still having trouble with the spring, and I'm not sure if this is a remote sensing of greenness problem or something else yet. We're working on that, but there's a lot more photosynthesis in the early spring compared to either one of our optimized models versions yet. So last, I'm going to talk about, second to last, I'm going to show you just a quickie on surface energy balance. I forgot. But the last substantive topic is watching the corn grow. And you might say, what's the purpose? We're studying urban fluxes. Why do we care about the corn and soybeans surrounding Indianapolis? The reason we care is that what blows into the city, our background conditions are in CO2 are governed by those rural ecosystem fluxes. And I'll make the case that if we don't understand those rural ecosystem fluxes, we will not be able to interpret our mole fraction data from the city. We must understand that in order to do a good job with our urban budgets. And here's an illustration. This is a nerdy one. I'm going to take a minute to dive into this. This is from a paper from Tasha Miles in Carbon Balance and Management that was just published. And on the vertical axis is all of our towers around Indianapolis. And this is aggregated over many years. And on the horizontal axis is month of the year. And what's colored in is the difference in CO2 between a background tower and the tower of interest. And these are conditions when, at least for the background towers, they're not in the urban plume. And these down here are the background towers. And I've blotted out the urban towers for the moment for a purpose, because I want to focus on the background towers, especially initially Tower 9 and Tower 1. Tower 1 is in a forested region. All the rest of this area is agricultural. This is forest, this little quadrant here. So Tower 9, which is a background tower, is in ag. Tower 1 is in forest. There is a difference between Tower 1 and Tower 9, which is, you can follow along this horizontal bar for Tower 1, which ranges from -3 to almost +3 parts per million. That's at least 50% of the amplitude of the enhancement in CO2 we see in downtown Indianapolis. So if we had only one of these towers and the wind came from the east and then came from the southwest, we would make an error in the background of the same magnitude as the urban enhancement, and we would get a dead wrong result for the urban emissions. And just to bang that a little more, this is winter, summer enhancement with all the towers in the city. And so in the summer, the increase in the upwind, downwind difference, it's up to 4, 5, 6 parts per million compared to about 2 or 3 or 1 in the dormant season. That's not because the emissions in the city have increased a lot in the summer. That's because the biosphere around the city is highly active. So we must understand those biosphere fluxes to get the city emissions right. Tasha explained the Tower 1 to Tower 9 difference quite nicely in this paper in 2021 by looking at flux towers around the city. We borrowed Monroe Morgan State Forest, which is a forest site, that's the dark green, and compared to corn and soybean from nearby Illinois. We're making our own now, but we use this at the moment. And you can see that the forest drawdown happens sooner than the agricultural sites. And that corresponds with the Tower 1 to Tower 9 difference being greater at Tower 1 early in the season when the forest starts photosynthesizing. And then Tower 9 catches up and has a big delta after the agricultural system starts photosynthesizing. So that appears to explain the basic difference, the difference between corn, agricultural, and forest phenology. We get at that with the flux towers. So they are complementary. They inform our understanding of the urban greenhouse gases. I'm going to point out now the puzzle we're working on now, which is Tower 9, which is agriculture, and Tower 14, which is agriculture. And the difference is very large, as much as -3 to -4 parts per million lower CO2 at Tower 14 compared to Tower 9. And that's not caused by the city. We filtered out those wind directions. When we first thought that, Michelle would appreciate this, Tasha Miles and Scott Richardson thought we had a leak in our inlet and there must be something wrong. We checked, double checked, triple checked. This is correct. So we have a couple hypotheses. One is that there's more corn to the west than to the east, or that the corn is more productive to the west and to the east. Corn photosynthesizes like gangbusters. So we've started putting out flux towers in the corn and soybean ecosystems around the city to try to sort this out, east versus west. We're still in progress, but we're evaluating the VPRM model to see if it can simulate the flux tower measurements that we collect in these different agricultural sites. And if so, then when we use that ecosystem model outside the city to try to interpret our mole fraction data, does that model explain these complicated features in the urban background? if we have a model to describe the urban background, then we are better off at understanding the urban emissions. Long story, but important. So the last is a really simple example. Obviously, we need to understand atmospheric mixing and transport to understand urban greenhouse gas mole fraction data and urban budgets. And urban eddy covariance has been used for a long time to evaluate the momentum and sensible and latent heat fluxes that drive turbulence and atmospheric mixing. And we can do that with these measurements as well. And so we have just one simple example, kind of a simple story. We published this a ways back. We noticed that if we compared our default model, which was in light blue, I'm focusing on the lower right set of panels, and there's too many lines here. I want to draw your attention to this light blue versus black, which is observed. And this was Tower 2, that site I showed you at the very beginning. The modeled sensible heat flux was much greater than observed, factor of 2. So what's going on there? So the first thing we checked was the land cover. And the land cover was quite wrong. WRF's, the weather research and forecast model, the weather model that we use for this, its default back in those days, it's been updated, I think this has been fixed, was that if you had a square kilometer of land surface, the land cover data that was the most common would be used as the land cover data for that square kilometer. And in the city, the most common land cover is developed. And so WRF default would make the whole city pretty much a parking lot and get largely zero latent heat fluxes, which was the dominant problem here. So we developed a tiled land cover system, and you can see that the land cover fraction goes from it's either 0.5 or 1 here, becomes much more modulated in this 30-meter resolution land cover product, actually becomes less urban because a lot of US cities have a lot of green stuff in them. And then that improves the sensible heat flux, drives it closer to the observations, doesn't fix it. But this is more important, I think, than all the different urban canopy model boundary layer combinations we experimented with. Basic land cover was the most important issue. So conclusions, I think with the appropriate decomposition methods and tower placement, these are extremely useful measurements for understanding urban greenhouse gas emissions. The work is complementary with atmospheric budgets and the inventory systems. And we are using this to improve our models of both the anthropogenic and the biological system. And also we need to do this to make sure we have the right meteorological drivers. And this is exactly the same reasons we're doing this in rural systems for biological fluxes. We need more of these measurements. We need advances in flux footprint models. You have Encore Decide coming up in a couple sessions to talk about that. Tracer ratio methods, understanding and being able to decompose is important. We've started, I wouldn't say that this is done. We need the high resolution models to compare to. We're lucky that we have Hestia in Indianapolis. We need to build this similar systems in biological flux models. And I would argue that we really need to keep these tower measurements, concentration towers and flux towers in the same places. They can work together. It's not either or. We should be working with both. And there's a stack of citations in case you're interested. And that's the end of my presentation. Thank you very much for your attention. I'd be happy to take questions. Andreas, I see you chatted a question. Looks promising to use CO2 ratios. Do you consider the ratio to be similar? No, it's not the same ratio for home heating as for traffic. That's a good question and an important problem. And we have used an aggregated R value that mixes them together. We've experimented with changing the range. If you change the ratio, you obviously get different total fluxes. The temporal patterns don't tend to change much. The spatial patterns would change. We need more research on that. I've been dreaming about flask sampling by wind direction to try to pin down directionally dependent tracer ratios at a tower. We can't do continuous 14 CO2, obviously, not yet. Maybe someday. We can do continuous CO. So Yeah, Andreas, that's still a problem we need to work on. Any other questions?
You can also raise your hands and just say your questions aloud.
Yeah, Dominic, I agree. I'm stunned by the temporal agreement between the Hestia and the measured fluxes. I suspect that the dominant contribution is traffic data, and Hestia does incorporate relatively continuous live traffic data. I suspect that's it's usually road counts. I think it's not phone data, it's road counts available in the cities. Kevin Gurney's the expert on what they bring in there though. But yeah, it's stunning. Hugo, please.
Thank you very much. Very clear presentation. So
Thank you.
I enjoyed it. I have a question regarding your quantification of the background that you say. That's really important, because if you have the one side of the city, you have a different system towards the other side of the city. But I was wondering, that still seems like I mean, I can really understand it, but it seems like a pretty huge effort to do this. If you have, I mean, now you have forest and you have corn, you might have more. I was wondering, isn't it enough if you monitor the mole fractions there, instead of trying to do this, understanding completely the flux, which is much more complicated?
Yeah, I would agree. If you had a very good ecosystem model or a very comprehensive background monitoring system, either is probably sufficient. Which one is easier or to come up with, I'm not certain. And
yeah,
so,
that would be the question, of course. It's more a question of, well, resources and what gives the
yeah, we would not have
suitable answer.
we wouldn't have known about this problem though if we didn't have multiple background measurements. And so, you know, we're experimenting with how to do this, and we said, oh, how can this be? They're both agriculture. This doesn't make sense. Ultimately, maybe down the road we don't need both, and we can get away with less. But for experimentation,
that's clear. That's clear.
Gotcha.
There was this one question earlier in the chat that you said that you would come back later. What was it? It was about what was it now? Somehow
it was
combining
it was Michelle's question about the reduced emissions on weekend and vacation, and
no, it wasn't that. It was
no, not that one, a different one.
What was it now? Sorry.
I got them all, but I might have missed somebody. Please let me know if I didn't answer your question.
I think that was the question from Gara, but he went back for that in the slide. That is, I think.
Yeah.
No, sorry. I guess it was the plot that you show on the photosynthesis that the delay. You remember at one point when you compare one of the first slides that you presented, there was this strange pattern of photosynthesis that was quite delayed, but I guess you answered also with the mice then later.
The winter photosynthesis, if that's what.
Yeah. Oh, yes, exactly.
Yeah, it was the winter photosynthesis, which I'm arguing that since we then put these flux towers out in turfgrass and saw turfgrass photosynthesis in the winter, that we think it's correct. We initially thought maybe we have an error in our decomposition, and I still can't, you know, absolutely prove it, but it seems very consistent with the photosynthetic activity of turfgrass in the winter.
Aren't winters really cold in Minneapolis?
Well,
minus degrees.
They do get that way. By the time you get to January or February, they can get certainly below freezing, and there is often but not always snow cover.
Yeah, and still photosynthesis. That's quite
well. When it's frozen solid and there is snow cover, the fluxes do become quite small. But if it's, you know, and I've told people, if I go out in my yard here and there's some snow cover and I brush the snow off, the grass is green. The turf grass does not turn brown. And so I think as soon as you get some moisture and sunlight, this stuff's ready to go. It's a cold season plant. Seems to be.
Yeah.
Andreas.
Questions, yes.
Yes, so very nice talk. Thank you again. I was wondering, in the test beds you showed from the US, 3 of the test beds are coastal cities. In ICOS, we have only continental cities. So are coastal cities easier from an inversion perspective, or are they more challenging?
No, they're harder. They're harder. So of the NIST test beds, it's Indianapolis, DC, Baltimore, and LA. And so 2 of those are coastal, and I would argue that they are considerably harder. And LA has the added problem, of course, of the mountains. Baltimore, Washington has the problem that it's in the middle of a metropolitan strip. NIST is ambitious. That's my answer to that. They want to go for it. Indianapolis is the simple case. We started with the simple case. Yeah, and the other cities are just investigator driven, not a central design. Samuel.
Hi, Ken. Thanks for your nice talk. I have one practical question. You had a quite tall tower in Indianapolis, something like more than 100 meters. Yes. And you decided to put your eddy-covariance around 30. So what was that decision based on?
So I've got a long history of really tall flux tower measurements. I started out with the WLEF tower in Wisconsin, where our top measurement was 400 meter level and the lowest was 30 meter. What you get with higher altitude is a larger flux footprint, but you're more often decoupled from the surface at night, and it's difficult to use the data. So we went for a lower measurement in order to get a more modest flux footprint. We didn't need one that was huge, and more consistent day-night coverage. But you could make arguments for either one. Yes.
Thank you.
You're welcome. Ingeborg, greetings.
Yeah, hi everybody. Thanks, Ken, for this excellent talk. Very interesting. You
Welcome.
just made internal eddy-covariance fluxes. Isn't that a headache?
Isn't it? I don't think the eddy-covariance fluxes are a headache. In fact, I would argue that they're much simpler than the inversion-based fluxes.
Yeah, okay. The nocturnal, I mean.
Oh, the nocturnal fluxes are a problem, sure. And we do have to look for very stable conditions and filter out the stable conditions because they may not be coupled to the surface, or we may have drainage problems. Yes. So you do lose some data without question. In the city, it's a rough system with an urban heat island often. I think you get more turbulence at night than you might outside the city sometimes. So I think we might lose less data, but yeah, none of these systems no method is without its headache. And yes, we do need to worry about the nocturnal loss with eddy-covariance. It is not a panacea.